Alright folks, today we're finishing up 10.2. We're going to talk about how what we did last time with Pascal's triangle actually applies to probability. So we are specifically going to focus on what are called binomial probabilities, or probabilities with situations that have exactly two outcomes. So things like flipping a coin, true or false questions, or really answering any type of question as long as you classify it as right or wrong, and really anything that can be classified into two options, like living or dying, success or failure. This is the most common we'll think of, what we want, and its complement, the leftovers. Okay, so what we're going to talk about first is coins, and then we'll relate it to the stuff last time. We've got 3 coins, a penny, nickel, and a dime, and we're tossing them and we're writing down what we see, heads or tails. Okay, this is the same thing as flipping the same coin 3 times. We're listing out the outcomes. Okay, we've talked about this already, but make sure you stay organized. We're going to have heads, heads, heads first. Then we're going to do all the ways to get 2 heads. So we could do the 2 heads first, and that really means 1 tail. So then we're going to move that tail to the middle next. Then we could have the tail come first. Okay, so we've got all 3 heads, then we've got the 2 heads, then we want to look at 1 head. It could come first, it could be in the middle, or it could be last. And then no heads looks like tails, tails, tails. So there's 8 possible outcomes. We should have known this ahead of time because heads or tails repeated for 3 flips is 8. Okay, but what we're going to do is look at the formatting of these outcomes. Okay, if we talk about rolling 3 heads, we ended up having the same thing that happens on 3 of Pascal's triangle. Okay, so grab that out for me. And what we're going to talk about is that row first, the total. So if you look at row 3, it's got the numbers 1, 3, 3, 1. If you add those up, you get 8. But these numbers go back to our sample set that we were just talking about. So here, there was 1 way to get 3 heads. There were 3 ways to get 2 heads. There were 3 ways to get 1 head. And there was 1 way to get no heads at all. So here, the probability of rolling 3 heads, we know there was exactly 1 out of the 8. 2 heads, there was 3 out of the 8. 1 head, there were 3 out of the 8. And 0 heads is 1 out of the 8. These probabilities represent really the expansion of a binomial. So what we can do is think about heads plus tails. And this first one means, remember, h to the 3rd power, or 3 heads. The next one goes with h to the 2nd power. Well, if you have h to the 2nd power, then the tails would have to be to the 1st power, and we've got a total of 3. Okay? Then the next one says heads to the 1st power, tails to the 2nd power. And the last one is our 1 going with all of the tails. And if we use this, then we wouldn't necessarily have to list out the sample space, and that's why it's so powerful. Before this time, the only options we had for probabilities with past exactly 1, like all right or all wrong, okay, the only options we had were to list and count. Now, we can look at Pascal's triangle to interpret it. Okay, so let's try this here. A coin is flipped 5 times. If we think about 5 times, we want to do 2 to the 5th, heads or tails, and that's 32 outcomes. But again, If you go look on your fifth row and add together the coefficients, that represents the 32 different ways that the heads and tails can be combined. Okay, so go ahead and for me, if you would, write out the row here for your fifth one, because we're going to answer the questions on these ones with it. So 1, 5, 10, 10, 5, 1, and we can see really clearly that that really is 32. But again, we're going to talk about what it means. This one goes with heads to the fifth power. This one goes with heads to the fourth power. This one is heads cubed, heads squared, heads to the first, and 0 heads. So if we want to find the probability of exactly 3 heads, we're just going to use these two things together. 3 heads went with the number 10, so the number 10 goes on top over 32. All we have to do is reduce that thing. Okay, exactly 4 heads went with the number 5, and that one can't reduce. At least 3 heads would mean 3 or more, so it'd be all of these ones, 3, 4, or 5. We'll go ahead and write that down. And that ends up with 16 over 32, which is a half. And at least 4 heads just takes the 5 and the 1. So 6 over 32 can reduce to 3 over 16. So instead of listing and counting, we can do this very, very quickly using Pascal's triangle. So my question is, can you handle this for 6 times? Okay, I want you to pause the video and try this one. Please list out the row and write out your powers like we did on that last one. Alright, so here we've got our row. There are 64 total outcomes. I'm still going to use the power version rather than counting these up, but counting those up will still get you that same answer. Exactly 3 heads was heads to the 6th, heads to the 5th, heads to the 4th, heads to the 3rd. Okay, so there. And 3 heads, I went this direction, but there's symmetry with this. Just like the same way, I didn't necessarily have to call this heads first. I could have said tails to the 6th, tails to the 5th, and so on. Either way, they're adding up to 42 on top, and then both of those reduce. Okay? But what we want to be able to do is also generalize this in what's happening as a binomial to introduce what's called the binomial theorem. Okay, so I've listed out the outcomes for 2 coins and for 3 coins, so my sample space is there. And old school way, we just counted how many outcomes worked and put it over the total. We just talked about how Pascal's triangle can help us figure out that top number, but I also want to talk about this old school way. Okay, when we're talking about flipping 2 coins, we've got the first coin and the second coin. And when we're talking about the first coin and the second coin, we can talk about there's 2 for the first, 2 for the second. That's why 2 squared gives us the 4 total outcomes that work here. We could also use that for probability. So with probability, what I'm going to look at here is just 1 heads. Okay, so to get 1 heads, we have 2 different ways that could show up. Okay, so this is important, and this is a piece we haven't seen yet. Okay, I'll talk about it more here in a minute. This part we've done before. When we're talking about flipping 2 coins and we want one of them to be heads, that's saying one of them is going to be heads and the other one has to be tails. So 1/2 times 1/2. But if you look at our sample space, and that's why I listed it out, there were 2 ways for this to happen. 1 heads or 1 tails is the same thing as flipping those around. The tails could come first, then the heads. So there were 2 different ways to have that happen. Okay, if we expand that to 3 coins, we've got 3 blanks. If we want one of them to be heads, that's 2 of them have to be tails. And why this is important here is because we want to be able to do this for any number of outcomes and generalize this pattern. The number of trials is going to be our number of blanks, but hopefully you're recognizing here that this is really just the probability of heads, however many times you want heads to happen, and the probability of tails, however many times you want it to happen, or 1/2 one time and 1/2 two separate times. Yes, we can put these together, but I want to generalize when it's not equally likely for both. This number, though, we haven't talked about yet in terms of how we get it without a sample space. We just said that Pascal's triangle can help us, so I'm going to go relate that back to Pascal's triangle for a minute. 3 coins is third row, 1, 3, 3, 1. If we want one of them to be heads, then we go to 3 heads, 2 heads, 1 head, and then pull that number down. So let's do this for 9 coins. If we want 1 head in 9 coins, that would mean that the first one had to happen 1 time, and the tails, which is still a probability of half, have to happen for the leftovers, the rest of them. What I want you to do is go to Pascal's triangle, the 9th row, and find out which would go with 1 heads. Hopefully, you find the number 9. Meaning we could type this in and get our probability of 1 head without listing the sample space. Okay, and that's important in general. Yes, we could do this without using this method, but we're going to need this method for the binomial theorem when they're not the same. I want to relate this to our binomial theorem that is listed on the back side of your paper, but I show you here because we'll see it on the back as well. Okay, here's what's happening. You're taking the probability of what you want, raised to the power of how many times you want it, and then the leftover probability, raised to the leftover number of trials. And once we practice doing different problems, this is going to be really easy with the pattern. But what we haven't talked about yet is what that number on Pascal's triangle is really representing. We've seen it in our sample space, but I want to talk about it in terms of the language we've used earlier this chapter, and that's with combinations. On your homework last time, I asked you these questions. I said list row 5 and then list these combinations, and hopefully you noticed that they were the same. So when we're talking about our expansion, I'm going to go back to coins. This combination ends up being the first number because we're talking about 5 coins and we want 5 of them to be heads. It's a combination because I don't care where the 5 heads are, I just need them to happen. So it's 5 choosing 5. Same thing here, this is 3 heads from 5 heads, and that's a really quick way for us to get that number in front if we don't have Pascal's triangle handy. Okay, so we're going to practice with both ways moving on. Here's our first example. It says the probability for a certain cancer to remain in remission for at least 1 year after chemo is 0.7 for all patients with that particular cancer. We want to find the probability that exactly 2 of 4 patients being monitored can keep the cancer in remission for at least 1 year. So there's 2 options, and we're going to use the independent method, or the fill out your blanks, to get this done. Okay, we're going to have a number in front representing the number of ways, and then we're going to have our probabilities classified into their 2 groups. These are binomials because there are 2 options. In this case, it's going to stay in remission, or it's going to not stay in remission. It's a pass or fail. So our first parenthesis is going to be given that probability that we see, and the second parenthesis is going to be the leftovers, so that would be 0.3. Then we're going to go to what our question is asking to be able to fill out our powers. We want exactly 2 of the 4 patients to actually be in remission. So 2 are in remission. And it says 2 of the 4, so we have to make sure that the leftovers add to 4. So there's 2 then who wouldn't be in remission. On Pascal's triangle, since there are 4 patients, we would go to the 4th row. So that would be 1, 4, 6, 4, 1, and then we figure out the number that goes with this power. So looking for this one, if you want to write it out with powers like we did with heads and tails, this would mean remission all 4. This would mean remission 3 of them. This is remission 2 of them, and so on. So we want the remission to be 2 of them, so the number 6 goes with that. And then all we have to do is go type in that probability. So 6, then 0.7 raised to the second power, and then 0.3 squared as well. So our probability is 0.2646. Okay, but I told you this number represents a combination based on this statement right here, and usually that's honestly easier to write out. I usually only use Pascal's triangle when using equally likely outcomes, like the heads and tails problems we were doing, or if we see something like at least, and I'll get to that in a minute. Okay, so a combination, we start with C, and just like we had before, we always start with the total number. So our total number is 4, and we want 2 of them to be in remission. If you type that in, it'll give you 6. Okay? The rest of the thing stays the same. We still want 2 in remission, and we will still want our leftovers, 0.3, to be our leftover people, too. Okay? The only difference is how you would type this in your calculator, and you can still put it all in the same part. Remember, with combinations, you start with your number, then go over to your probability, number 3, and that is 2, and then you just say times the rest of it. Okay, so 0.7 squared and then over to the second one, 0.3 gets squared as well. And they're equivalent. Your choice. Alright, this one says 2 or 3 patients can sustain. The word or means add. And we are going to add them up doing the same process we did on this one. We're starting with 2. So I want you to set this up. 2 patients, 3 patients, because we're going to have to do this process, one or the other, doesn't matter, twice. Okay, I told you I liked Pascal's triangle when we have more than one or an at least problem. Okay, this is an or problem. It's another time where I prefer using Pascal's triangle, because if I don't have to type this in for multiple things, then it's actually faster to use that. Okay, we already wrote down the row. We already realized what each of these numbers mean. We want to find the one that goes with 2. Okay, the one that goes with 2 we've already done. Okay, this comes down. Our job is then to just do the one for 3. So looking back up here, the number in front is 4. 0.7.3 happens, but it says 3. So our first number is 3, and I know they have to add to 4. So that one has to be the leftovers of 1. And then you can type this whole thing in your calculator as is. Okay, I already have this number, so I'm just going to say plus, and then 4 times the 0.7 getting raised to the third power, and the next one, 0.3, is the first power, for a total of 0.6762 of a probability. So really pretty likely. Okay, it's over half. Okay, we'll do this a few more times because it takes a while to get the hang of how the pattern is showing up, but once we get the pattern, they will go really fast. Alright, 8 multiple choice. We have to do Pascal's and combination for here on your homework. I really don't care which one you use. Okay, so 8 means the 8th row. What I want you to do is write down your 8th row of Pascal's triangle. I'll give you a minute to do that. And then what we're going to do is look at how we can find the probability of getting 5 of those 8 correct. The last time when we did problems of probability like this, we were only capable of finding the probability of getting them all right or the probability of getting them all wrong. With the binomial theorem, we can find the probability of any number of correct questions. Okay? So we've got our row written down, I hope, and we're going to talk about what this means. It says we've got 4 alternatives, A, B, C, D. So that would mean the probability of getting the first question right, or any of the questions right, is 1 out of 4. So we're calling that the probability of success, or when we're writing out our parentheses, the thing that goes in the first number. Failure is the leftovers, or the complement. There are 3/4 left over. So we're starting out both of these the same way. In your bubbles, you're putting the probability of success, probability of failure right next to each other. Okay, then your powers come from what it asks. We want 5 correct, and we know it has to total 8, so there's 3 left over. 5 correct means 3 are wrong. And then this could happen in a lot of different ways. I could get the first 5 right, or the last 5 right, or some right in the beginning, some in the middle, and some at the end. So that's where the first number comes into play. It gives us the number of ways this could happen. So Pascal's triangle can give that for us. Okay, I had you write the row. And we're going to talk about how to find 5. So remember, this is correct and wrong, or right or wrong. So this is right all 8, right 7 of them, right 6 of them, and 5 of them right, and that's what we want. So our 56 would go out front. Now, this seems time-consuming, but remember, I only need you to write that on the practice. On your homework, I don't need to see that. Okay, you can, on your practice, or on your Pascal's triangle, go 8, 7, 6, 5, and then throw that number in front, and you're done. Okay, so it is a shortcut as long as you can read what it means. Over here, how we could get that 56 using a combination is just thinking about, I have 8 total questions, and I want 5 of them to be right. Very straightforward, just a little tougher to type in. Okay, let's go ahead and type these in. 56, we wanted 0.25 as a fourth. We wanted 5 of them to be right. Second part are the wrong answers, 0.75. We wanted 3 of those. So our probability looks a little messy here. We'll try math inner to see if it's a nice fraction. If you cannot write it as a nice fraction, even though this is a rational number, promise, we're going to round to 4 decimal places for these. Okay, if you can't write them nice, 4 decimals for rounding. So 0.222. Alright, next one should be exactly the same way. I'm not going to type this whole thing in, but I will just show you the first part. If I go over to the combination and show you 8C5, it really is 56. Okay, so this is handy without using Pascal's. Okay, now it says 6 or more correct. So 6 or more correct would mean 6 would work, 7 would work, 8 would work. And there's 3 different outcomes for that one. So first step, is the 6. Second up is the 7. And last is the 8. And remember, when there's more, you just add them. Okay, let's use Pascal's triangle because it's there. 6 correct is 28. 7 correct is 8. And all of them correct, there's only one way, we know that. So we've got our 1/4 to the 6th power. If 6 of them are right, that means 2 of them are wrong. Here. This is our 7. So then our leftovers is only 1 there. And then lastly, 1/4, all 8 are right. That means none are wrong. You can cross that part out. Okay, remember if it's a 0 power, we always got rid of it. And then you just type that whole thing in. Okay, I'll give you time to do that. Pause the video. Again, for this one, if it's not nice after math inner, you just round to 4 decimal places. I want to show you one more way to do this because this is not fun when there's more than 2. Okay, so your calculator has a shortcut, and this shortcut is on your note card as a reminder. Okay, it is the binomial. Under your calculator, it's PDF. That stands for probability distribution function. Okay, so what we're going to do is use this to add up 6, 7, and 8. We have to go to 2 different places on our calculator. Again, the instructions are on your note card. We're starting with second stat, so hit that for me. Going over to math, and that is where the sum function is. So it lets us add stuff. Then we can actually grab that binomial PDF that I was talking about, and that's under distributions, the second bars. Okay, scroll, and it is A. We want to use this one. This is the probability distribution function. This is the cumulative one. We don't want that. Okay, the first thing you are going to type in, whether you see this screen or not, is your total. So our total value was 8 questions. If you see this screen, you just have to go down. If you don't see this screen, you need to place a comma instead. Okay? The next thing you're going to list is the probability of success, and ours was the 0.25 or the 1/4. Again, if you see this screen, go down, but if you don't, use a comma. And the last thing is these outcomes that we wanted to be successful. We said 6, 7, or 8. Because there is more than 1, we have to use set brackets. They are above the parentheses. Hit second parenthesis and list them. 6, comma, 7, comma, 8, and then close your parenthesis. After that, you hit enter until something pops up. This is how you were typing it with your commas if you didn't see that screen. And that gives you the same thing as doing it by hand without as much work. Okay? You are only allowed to use this shortcut if there are 3 or more. If there's 2 or if there's 1, you gotta do it by hand. That shows me you know the math behind what's happening to get this probability. Alright, we're going to do one more together, make sure we understand it, and then I'll let you try one on your own. Okay, 6 and 7, it says the probability of a heart pacemaker working flawlessly for 1 year is 0.92, and that pacemaker is given to 6 patients. So this is our total value that we're working with. Okay, that's also Pascal's triangle row if you want to look there to calculate this. Alright, so we want 5 of the 6 to function flawlessly. Okay, so we know our bubbles have this probability, 0.92, and the complement, 0.08. I know that this is my power 5, and it has to add up to the total 6, so there is 1 that is not working. Where you get to choose is how to find the number in front. Okay, 1 is looking at this row on Pascal's triangle, and the second option is using combinations. Okay, on Pascal's triangle, 1, 6, 15, 20, 15, 6, 1, you would want to find the one that represented 5 patients. Here is 6 patients, that would be 5. Option 2, using a combination, our total is 6, and we're choosing 5 of them, it still gives you 6. It does not matter. Okay, this one is straightforward, but you type it in more. This one, you have to find it, but then once you find it, you see the number and you don't have to type in as much. Your choice. Okay, go ahead and type that into your calculator. And we should get about 0.3164 for our probability. On the next one, it says at least 3. So that would mean 3 or 4 or 5 or 6. This is 4 separate ones. This is one we get to use the shortcut on. Okay, so I'm going to remind you on how to type that in since we did our last one the first time. With the shortcut, I do want you to write that out. I need to see it. Put set brackets around it. And we're just going to literally write on our paper what we're typing into our calculator, and that's how we'll show our work. Okay, so that goes last. Remember, the probability goes in the middle, and it's just the success one. So it's the 0.92 for us. And then the first thing is our total people, in this case, was 6. So we're doing the sum of the binomial PDF, and you can abbreviate that however you want. I usually just do bin PDF and then parentheses. Okay, so on our calculator, let's do it. If you actually have this in your calculator, do second enter and just edit stuff. But I'm going to show you again, and for right now I want you to practice it again because we need to get the repetition here so we remember the process. Okay, let's redo this one. Okay, so first step, we're hitting second stat over to math. Second stat over to math. Scroll down to number 5. Then we go second varse. Find the binomial PDF. Scroll. Trials go first. We said that was 6. Comma, if you need to. Then this one is 0.92. Comma, if you need to. Everybody has to use set brackets. It will not work. It'll give you an error message if you don't. So 3, comma, 4, comma, 5, comma, 6, and close those. So this one is very high chance for this to happen because our probability of 0.92 is likely. Having 3 or more working is very, very likely. It is about 0.9995. 4 places for these ones always. Okay. So what I'm going to have you do is make sure that you can handle this for these 4. Okay. Hopefully we've had enough practice where the process goes pretty quick. Pause the video and try those for me. First one, we wanted 8 right, which means 2 wrong. 45 ways to do this, either combination or Pascal's triangle. Next one, 9 questions correct, so 9 right, 1 wrong. 10 ways to do this, Pascal's triangles, or combination 10C9. This one would be 10C8. Anytime I'm answering multiple questions about the same thing, I'm going to use Pascal's triangle. Okay, this one, 6 or 7, you have to show your work for. First one or second one, you split them up. Here's the 6, here's the 7, and add them together. You can type that whole thing in your calculator in one go after you've set them up. The at least is where you get to use the shortcut that we just talked about. There are 2 ways to answer this. Let me talk about all of these weird problems. They did end up being scientific notation, but these ones you didn't have to round. There were 4 digits after the decimal point, not more than that. It was exact, so hard equal sign there. Okay, same thing with here, just scientific notation. This one, we did have to round, but it wasn't scientific notation. On number 11, it came out with scientific notation, but this one there were more than 4 decimal places, so you can round it. I like to, if this number ends up having 4 or less, like -1, 2, 3, or 4, then you can actually switch it to regular form, and that gives you a more realistic probability of what's actually happening. They're equivalent, but this tells us really small, close to 0, not very likely to happen. Okay, so you are allowed to use this shortcut only if it's more than 2, or at least. You are not allowed to use it on problems like 10 where there are exactly 2. You have to show your work. Okay? If you do struggle with anything, typing it in or understanding how to set these up, please come see me.